So we're on to, hopefully, last lesson. You filled in these. I think most people sent me pictures of that, even though I didn't ask them. But brilliant. Okay, so today we're going to look at measurement of distance with ultrasound. Okay, so you often get measurements of distance with ultrasound. It could be if you're looking for underwater for any objects. It could be imaging a baby or finding something within the body. You wanted to know how far in it is. Or it could be an industry. You want to see if there's any faults anywhere. You could use ultrasound for all these kind of things. So I don't have the ultrasound transmitter out today, but basically what it is it's an ultrasound transmitter and an ultrasound receiver. This sends out ultrasound, it gets bounced back off a metal plate or whatever it is you want to find the distance to, and it gets received here. And on the oscilloscope, it shows you a peak where it gets transmitted and a peak where it gets received. Okay, so obviously this is it's a little bit like an echo if you could hear it. So it goes there, bounces and comes back again. So we've got it going there and back. So on the oscilloscope you would see a transmitted pulse and a reflected pulse. And that tells you the time that it was transmitted and that tells you the time that it was received. So you could find the time between the two, and that would be the time it takes to go there and back. Okay, so the second peak, which is due to the reflected pulse, is smaller than the first peak, but only a part of the transmitted energy is reflected back to the receiver. So basically, energy is lost. So after it's been sent out and it's come back, there has been some energy lost to the surroundings. Okay. The distance on the screen between the two peaks is used to find the time taken for the ultrasound to travel from the transmitter to the metal plate and back to the receiver. And knowing the speed of ultrasound, the total distance from the transmitter to the metal plate can be calculated using distance is speed times time. So you can find the distance there and back using the speed of sound times by the time it takes to go there and back. Okay, so if you wanted to find just the distance there, then what you're going to have to do? Divide it by 2. Yeah, you're going to have to divide it by 2. So the total distance there and back is the speed times by the time there and back. So if you wanted to find the distance there, so how deep something is in the water or how far something is away from you, you would have to divide that distance by 2. Okay. So, for example, I've got a result here that I would have if we had the equipment. The distance would be the speed of sound, because the speed of ultrasound is just the speed of sound, times by the time that it took. Now, I did an experiment last year and it took 3 times 10 to the minus 3 seconds. Okay, so if you do that speed, 340 times 3 times 10 to the minus 3, that comes to a distance of 1.02 meters. So that's the distance there and back. So the distance there would just be 1.02 divided by 2, so 0.5. So that's the distance there and back. The distance just there, 0.51 meters. Okay, so it's really important when you're reading questions, and probably there will be a question like this that comes up in any test that you do on waves. It's important that you read if it's going to be something that's there and back, or if it's just there. The clue should be in the question, in the number of marks that the question gives you. So if the question gives you an extra mark, so if there's a 4 marker rather than a 3 marker, that means that you have to do something extra. So remember your nuclear test, and I think there was like 3 X-rays or something coming, and most people, I think nobody times it by 3, but it was a 4-mark question. So if you give normal questions are 3 marks, equation, numbers, answer. If there's a 4 marker, you're going to have to do something extra in that question. So it's just a really big hint if you see 4 marks. So just keep an eye on the number of marks. Okay, so example. In an ultrasound scan, waves of a frequency of 5 megahertz, so that's times 10 to the 6 hertz, 5 million, are used. An echo, due to the boundary between soft tissue and a bone, is detected in a time of 150 microseconds. So that's times 10 to the minus 6. See how important these prefixes are? because they'll keep coming up again and again. The speed of the sound in soft biological tissue is 1,500 meters per second. So this is an ultrasound scan, probably of a baby. Okay. So first of all, calculate the depth of the boundary between the surface of the skin. So we know that it has taken 150 microseconds to go there and back. We've got an echo there and back. Okay. So time taken to go there and back is 150 microseconds. So 150 times 10 to the minus 6 seconds. The speed of the sound in soft biological tissue, so within mother's womb, is 1,500 meters per second. And it's asking us to find the distance, but it's asking us to find the depth. So we only want to find the distance there. Okay, so it is an echo. So we'd have to find, first of all, using that time, distance there and back is the speed times by the time there and back. So 1,500 times by 150 times 10 to the minus 6. So distance there and back is 0.225 meters. But we don't want that distance, we just want the depth, so we just want the distance there. So the distance there is 0.225 divided by 2, so 0.113 meters. Alternatively, you could divide the time by 2 and just do distance there equals speed times the time there. Either is absolutely fine, as long as you're dividing one of them by 2. Okay. Leave that up for seconds, but you're very welcome to have a go at B. There's nothing new there while I wait. So for part B, we've got the frequency, we've got the speed, and we want to find the wavelength. So we're going to use the old familiar equation that should be by now, V equals F lambda. So speed is frequency times wavelength. So 1,500 equals 5 megahertz, so 5 times 10 to the 6 times by the wavelength. So the wavelength is going to be 1,500 divided by 5 million, 5 times 10 to the 6, which comes to 3 times 10 to the minus 4 meters. 0.0003 meters. Yep.
See, for B, so I put just the 5 million, so would that just be the exact same as?
Yeah, did you just put 5,000,000? Yeah, that's right. Yeah. Once you've written that down, what I want you to do is have a look at the past paper question that has that looks like that. So it's got like in the aircraft industry is the start of it. And I'm going to go through that one because I think it's quite useful to go through another past paper style question on this kind of thing. So just have a read through it. Yeah, if you want to have a go at it, you can start it, but I'm going to go through it. So, has everybody got that written up? Okay, right, I'll get the past paper. It's just a separate past paper on your desk. So in the aircraft industry, non-destructive metal testing is used to look for flaws in aluminium propellers. Ultrasound pulses, guys, are sent from a transmitter into the propeller being tested. If there are no flaws in the propeller, the ultrasound will be reflected from the back edge of the propeller, as shown in position A. The reflected signal is detected by a receiver. If a flaw is present inside the propeller, a reflection from the flaw will take place inside the propeller, as shown in position B. So we can see position A there. There's nothing in the way, so it goes there and back, all the way there and back. In position B, it's detected this flaw, so it only goes part of the way and then gets reflected back from there. Okay, so the first question: what is meant by ultrasound? So, oh yeah, go for it. Yep. So basically beyond the range of human hearing. So yeah, waves with frequency more than 20,000 hertz. I should probably say sound waves because they are sound waves. Okay, so that's just something that you need to learn. It's just a fact. Now the next stuff is just sort of analysing the question correctly. Okay, so this is the most difficult part of this question. So the graph shows the time taken between transmitting and receiving at points A and point B. So the time taken, obviously the time taken in part B will be shorter the smaller time, won't it? And time taken position A will be longer because it has to go further. Everyone agreed with that? So this one must be B and this one must be A. So it takes 5 milliseconds to go there and back for B, and it takes 12 milliseconds to go there and back for A. Is that clear? So this is the tricky part, is sort of analysing what's happening here. Okay, so one of those lines is that when it goes there and back for one of them, and one of them is when it goes there and back for the other. And it must be, the longer time must be A, because it has further to go. So, to B part I, state the time taken between transmitting and receiving the pulse at position B. So it's the one that takes the shorter amount of time, so 5 microseconds. Make sure your micro looks more like a micro than mine, microseconds. Is that clear? That is quite a tricky thing to sort of like work out. Obviously, we don't have a data sheet, but you would have a data sheet if this came up in a test. It says use the data sheet, that's this information right at the front of the test, to find the speed of the ultrasound waves in aluminium. So that's just something that you would read off the data sheet, and I'll just tell you now, it's 5,200 meters per second. Yeah, you get a mark for that. Only one mark, but yeah. It's testing your ability to sift through information and find the correct part. Yeah. Transmission to receiving, yeah. So the x-axis is the time there and back. Y-axis is just the energy. So basically, if it doesn't go as far, it doesn't lose as much energy. Yeah. Yeah. Right, part 3, calculate the distance of the flow from the front edge of the propeller. So it's one of these ones. So actually, this should be 4 marks. Because you have to find the distance there and back, because we've got the time there and back. So speed times time. The speed in aluminium is 5,200, and the time we just said for B is 5 microseconds, so 5 times 10 to the minus 6. So that should come to 0.026 meters, but we want the distance from the front edge of the propeller, so we just want the distance there. So it's going to be 0.026 divided by 2, which is 0.013 meters. And the final one, I'm sure you guys can do yourself, it's just a vehicles F lambda question, so have a go at that one. So you should get the answer here, 3.5 times 10 to the minus 4 meters. And if you're not getting that, please let me know. We'll try and work out what you've done wrong. Well, that's the same as 0.00035. So that's really the most difficult kind of question that you could get on this. So if you followed that through fine, then you should be fine with that kind of question.